Okay, so in this video I'm going to be using the binomial theorem to explore Beal's conjecture. This conjecture came about in about 1993 when a Texan banker called Andrew Beal was looking at the equation a to the x plus b to the y equals c to the z. And I've just changed the sign here for convenience. He wondered if there were any whole number solutions to this equation when all three exponents x, y and z are greater than 2. We know that solutions do exist when all three exponents are squared, because that's just the Pythagorean triples. But what happens when all three exponents are raised to the power of 3 or more? I'm using the binomial theorem, which is normally represented like this, where 2 terms to the power of n on the left can be calculated more easily by the formula on the right. And that's especially helpful when n becomes very large. When expanded, this sum has n plus 1 terms, with each with 3 standard factors: the coefficient, the unknown p to the power of n minus k, and the unknown q to the power of k. But we'll be using a new formula that I discovered, not for a single power to n, but the sum of 2 separate powers. And as you can see in the new formula below, the unknowns, a plus b and minus ab, are the same in form as the unknowns above. But it also has an associated factor, a to the x minus n minus k, minus b to the y minus n minus k. And if you pause the video, you might like to work out for yourself the final value for the right-hand side, for n when it's 1, for n when it's got a value of 2, and for n when it's got a value of 3. And you'll find the result to be somewhat unexpected. Well, if you've done that, you'll find that for all 3 values of n, the result is exactly the same, which makes n indeterminate, which means however large n becomes, it's always the same value, a to the x minus b to the y. And that's quite surprising. Since n is indeterminate, we can fix n as any value. So why not let n equal z, like this? We'll return to that in a moment, but meanwhile we're going to represent c in terms of a and b without their respective exponents. We'll use a plus b and minus ab as our fixed constants, and then introduce 2 variables, s and t, from the set of all real numbers to include fractions if necessary. And we can raise the power on both sides to get this for c to the power z, which in turn gets expressed in the bottom line as a standard binomial expansion. So if we recap for a moment where we've got to, we've now reconfigured a to the x minus b to the y in terms of z in a new binomial formula on the left, with that non-standard associated factor underlined in red. And on the right we've reconfigured c to the power of z in terms of a and b, with its own associated factors s to the z minus k and t to the k. We know the right-hand side is a power to z. The left-hand side may or may not be. We're going to assume that it is for values x, y, z greater than 2. That there are some whole number solutions to this equation out there somewhere. Both sides have the same number of terms, that is z plus 1 terms to be precise, and both sides have the same constant factors, a plus b to the power of z minus k and minus ab to the power of k, and both of these are standard in exponential form for a perfect power. But in our assumption, if we discover, using careful steps of logical induction, that for x, y and z greater than 2, the 2 sides are not equal, then the assumption will prove to be false. However, we're going to focus on the exponential form of the equation for a perfect power. For if the left-hand side can't even be represented in the correct standard form for a binomial expansion of a perfect power, as the right-hand side is, then there can be no equality of value either, while remaining a perfect power. So if we're testing only exponential forms in this equation, we can simplify the problem as follows. And now we can argue that if the Beal equation has solutions, then each and every term on the right-hand side must correspond exactly with its counterpart term on the left. If just one term does not correspond in form to its counterpart term, then not only will the integrity of that particular term be compromised, as a legitimate term in a binomial expansion, but the whole equation as an expansion of a power to z will be compromised. Now, using a simple proof by contradiction, we will first assume that the first terms on each side are equal and the last terms on each side are equal. From there, we will bring into play the second and penultimate terms and show that for x, y, and z greater than 2, it leads to a contradiction. So we can deduce the second term from the first term s to the power of z and the last term t to the power of z by raising the powers accordingly and multiplying together. We get the second term underlined in red. But also directly from the binomial formula, when k equals 1, we get the term underlined in yellow. Bringing these together and arranging, we get the equation in the blue box. Moving to the penultimate term, we follow exactly the same procedure. It leads to another blue box equation, and these two blue boxes are in fact very similar. Since the left-hand sides of these two equations, underlined in red, are exactly the same, we can subtract one from the other and rearrange to reach our final key equation at the bottom in the light blue box. You can see for yourself that solutions will exist either if the large bracketed fractions on both sides have a value of 1, since the outer exponents are not equal, or if the numerators to their respective powers on both sides are equal and the denominators also on both sides are equal. But since neither fraction equals 1, the first option is eliminated. And then the numerator on the left has to be greater than the numerator on the right, so this option also is eliminated. All of which means that our non-standard factor a to the x minus z minus k minus b to the y minus z minus k cannot be represented in the correct form for a perfect power, which means our initial assumption that solutions exist for x, y, and z greater than 2 is false, which means in turn that Beal's conjecture must be true. So what about the case for z equals 1 and z equals 2? Well, when z equals 1, the respective denominators and numerators are equal, allowing solutions, so no contradiction there. And when z equals 2, the large fraction on the left to the power of 2 is just 1 anyway. And the fraction on the right is top-heavy, but has an exponent of 0, so it equals 1 as well. So again, no contradiction. So by reconfiguring the Beal equation, we've effectively reduced the problem to one single exponent z. We've removed c altogether, and a and b with the respective powers have become mere bystanders. Whatever value we give to a and b and x and y, it doesn't affect the proof in the slightest. You can find all this proof written out in full at the web address below.